Question 6. The function g has derivatives of all orders, and the Maclaurin series for g is given by this formula right there. A. Using the ratio test, determine the interval of convergence of the Maclaurin series for g. So we want to go ahead and take this right here, and we are going to go ahead and, since we're using the ratio test, we're actually going to just be using the absolute value. So when we're using the actual test, we can ignore the alternating part of this problem. So when we use the ratio test, we're going to be finding the limit as n approaches infinity of x to the 2n plus 1 over 2n plus 1 plus 3 divided by, added 1 to my n's, it's a sub n plus 1 over a sub n over 2n plus 3. So if I simplify that, this is going to end up being x to the 2n, this will be plus 2 plus 1, so plus 3, over 2n plus 5. And then if I multiply by the reciprocal, it will be 2n plus 3 over x to the 2n plus 1. And then if I continue to simplify this, I can simplify my x's. The 2n's are going to cancel out, and if I subtract those, I'll get x squared times 2n plus 3 over 2n plus 5. And remember, we're finding the limit as n approaches infinity. So if I plug in infinity, I ended up getting infinity over infinity. So I get to use L'Hopital's rule, and I'm not sure still if that's spelled with an S or not. I still have to look that up. But anyway, we'll do the limit as n approaches infinity. Take the derivative. Remember, x is just a constant at this point in time. So the derivative of 2n is just 2. And the derivative of 2n down, plus 5 down below is 2, so those cancel out, so I just get x squared. And then remember, the absolute value of this needs to be less than 1. Okay, so if I do this, getting rid of the absolute values, remember this is just going to be negative 1 less than x less than 1. And notice that I dropped the squared, and it's because if I need, I still am going to have negative 1 and 1, because when I take a negative 1 and square it, I'll still get 1, and when I take a positive 1 and square it, I'll still just get 1. So this is my interval of convergence. However, remember that we do have to test the endpoints, so that's what I'm going to do next. So testing my endpoints, x is equal to negative 1, we're going to go back up into the original problem. So if I put negative 1 in for my x, I'm going to have negative 1 to the n, and then I'll have negative 1 to the 2n plus 1, and then it's going to be all over 2n plus 3. Okay, since these have the same bases, I get to add the exponents, so I'll actually end up getting negative 1 to the 3n plus 1 times 2n plus 3. And because this is an odd number, 3n, that will be alternating because of the 3 there instead of a 2 or something being there. So it's alternating, so since it's an alternating, I'm going to do the 3 steps for an alternating series. In the alternating series, u sub n has to be positive. And then in this case, u sub n is equal to just 1 over 2n plus 3 because we're ignoring the alternating part of it. So un is positive, that is correct. The second thing is that the derivative needs to be negative. So if I take the derivative of this, it will be negative 1, 2n plus 3 to the negative 2 times 2. So I'll get negative 2 over 2n plus 3 squared. So that derivative will always be negative, so I'm good to go. And then u sub n has to approach 0. So if I find the limit of that as n approaches infinity, I will get 0. So that does check as well. So since all 3 checks are met, the endpoint x equals negative 1, it does work. So we do need to put an equal sign there and there. So then let's check x equals 1. So when we do that, again, I'm going to go back up into my original equation. We'll get negative 1 to the n. We'll get 1 to the 2n plus 1 over 2n plus 3. And 1 to any power is just going to be 1. So this is really just going to be negative 1 to the n over 2n plus 3. So what we are going to do on this one, once again, it is an alternating series, and it's going to look, the u sub n is going to be just like the one up there. So because it's an alternating series and it does pass all 3 tests, it works as well. So this will be my interval of convergence. All right, we would get 5 points for that. So if we set up the ratio like I did right here, that would be worth plus 1. And then if I compute the limit of the ratio, which I guess would have ended up being x squared. So if you ended up getting x squared as your limit, you'd get plus 1. And then if you had everything before and you didn't worry about the equal signs at first, you would have gotten plus 1. And then if you considered both endpoints, so just even considering the endpoints was worth a point, and then actually correctly figuring out the endpoints, you got your last point. All right, part B. The Maclaurin series for G, evaluated at x equals 1/2, is an alternating series whose terms decrease in absolute value to 0. The approximation for G of 1/2 using the first two non-zero terms of the series is 17 over 120. Okay, and we're going to show that this approximation differs from G of 1/2 by less than 1/20, 200th. So they're really trying to trying to find that the error is going to be less than 1/200th. All right, we could go ahead and use the Lagrange error for this one. However, we actually have something that's called an alternating series error, which we have not discussed before, but it actually will be a little bit faster since this is an alternating series. The alternating series basically states that my error is going to always be less than the n plus first term. Okay, so my error, so the approximation, the difference between what it actually is and my approximation and actual G of 1.2. So I'm going to put G of 1/2 minus 17 over 1/20. So this is just standing for the error. You can just write error if you wanted to. We know that it has to be less than the n plus first term. So we're going to take the term. So they did the first two terms. So this is a first term, this is a second term. So we just need to show that the error is always going to be less than this term right here. So it's always going to be less than x to the 5th over 7. And we know x in this case is 1/2. So it's always going to be less than the 1/2 raised to the 5th power divided by 7. So we're going to now say that the error is going to be less than 1/2 to the 5th power would be 1 over 32 divided by 7. And that comes up to be 1 over 32 times 1/7, which is equal to 1 over 224, which is definitely less than 1/200th. So we have just shown that my approximation differs by less than 1/200th. So that would have been worth 2 points. If you used the third term to be the error bound, you would get a point. And then if you would show that it is less than 1/200th, you would get another point. All right, part C. Write the first three non-zero terms and then the general term for the Maclaurin series for G prime. So we already have G right here. Okay, and we would like to find G prime of x. So G prime of x, we basically just need to take the derivative because G prime is just the derivative. The derivative of x over 3 would be 1/3, and then minus the derivative of x cubed over 5 would be 3/5 x squared, and then plus the derivative of the next part would be 5x to the 4th over 7. So we did that, and then it also said to find the general term, so plus dot 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 plus. Okay, so now we actually have to take the derivative of our general term. Please keep in mind that x is the only variable, so everything else is treated as a constant and it will just tag along. So -1 to the n is just going to tag along, and then since x is my variable, the 2n plus 1 bumps out front, and then we're going to decrease the value by 1. So when I subtract 1 from my power, 2n plus 1 minus 1 is just going to be 2n. And then since the 2n plus 3 is a constant, it just tags along as well. So that is the general term. We would have gotten 2 points for that, 1 point for the first 3 terms, and then 1 point for the general term.